So return to equivalent capability, of course, is the foundation of legislation and regulations, particularly concerning land reclamation. These are legal concepts, and they're related to that. Soil scientists over the years have come up with metrics for attempting to measure land capability. Land capability is really a very simple approach to describing the value of soil. Take a very complex phenomena like soils and try to express it on a single axis, with one end being the most value and the other end of the spectrum being the least value for any particular land use. Of course, the legislation and regulations concerning capability are an umbrella concept over all kinds of different land uses and ecosystem values. With respect to soil capability, we originally came up with the Canada Land Inventory in the 60s as a way to define the value of soil. The most recent system we've got is called the Land Suitability Rating System from 1995. It's a federal government system, basically the work of a generation of scientists. And the short form for that is LSRS. But we've also developed a number of rating systems for reclaimed lands, all coming from the province of Alberta, where reclamation is more advanced, perhaps, than elsewhere. Terry Masick in 1987 built a system more or less around the Canada Land Inventory. In 1993, Len Lescu and his partner Kutash developed a little bit more of a methodical approach to assessing reclamation suitability or reclamation capability. And they modeled it more or less after the provincial agricultural system of the day. And finally, again, of course, Len Lescu has developed a system for use in the oil sands for forest land uses. Several versions of that. Well, I should point out that the legal system, the legal concepts of capability and the scientific reductionist concepts are not necessarily interchangeable, and I'm not even sure to the extent that the scientific ideas permeate the legal concepts. So they're definitely not interchangeable, and I don't know how much they interact. So the land suitability rating system, in Alberta at least, it represents our baseline soils. So if you look on the AgriSid soil browser, you can see for every soil polygon, the areas are broken down into the extents of each capability class. It's a fully indexed system based on climate, landscape, and soil, and every one of those starts off at 100 points, and then deductions happen from there. It includes both quantitative things that you measure very precisely in the field, and qualitative parameters, things that aren't quite so precise. And if you're applying this in the context of pipelines to see if they've been reclaimed to equivalent capability, I think it's acceptable to simply focus on the soil component of the LSRS system and make the, I think, reasonable assumption that the landscape is not going to change after pipelining, and definitely the climate won't have changed if you're comparing right-of-way and a control. The use of the LSRS system was in fact suggested in the 2001 draft reclamation criteria for pipelines. And I would credit that document with my inspiration for doing this study. The first thing I came up with when I wanted to study this was a lack of publicly available data. Without data, it's very difficult to calculate land capability ratings. I did find some data, PhD theses, master's theses, publications, but they were usually incomplete. They give me some values, some parameters, but not others. Some of it was just proxy or qualitative data, which is use it if you have to, but that's about it. So I chose the opposite approach. I developed my own synthetic data to explore the hypotheses. So my objective was to explore the degree of capability change in response to incremental changes in just a few key soil properties. So the parameters I wanted to work with, all quantitative: the organic carbon content of the topsoil, the depth of the topsoil, and the density of the subsoil. So 3 parameters, all based on numbers, units. I excluded anything related to soil chemical change, mainly because we have a really good 3-lift handling policy in the province, and I think it does a pretty good job. So I wanted to exclude those particular soils, at least for this version of this model. Doesn't mean I can't bring chemistry in later, but I also ignored the effects of compaction and texture on water holding capacity. So no matter the level of compaction I imposed on these treatments, I kept the water holding capacity constant, which means that the interim soil rating, basically the rating that the soil started at, was the same no matter what level of compaction. So I was kind of giving a leg up to the more advanced levels of disturbance by ignoring the effect of compaction on water holding capacity. And I guess I didn't have the time to integrate that variable into the picture. So if you've worked with the land suitability rating system, you know that it's a manual that has ratings tables, and for every particular parameter, there's a value of a parameter and then the rating associated with it. It's usually, if the soils are black, they get 0 points deduction. If they're gray, they get 5 points. That's not quite good enough for what I was working with. And so I had to take those various ratings tables and develop regression equations to explain those deduction points. And I suspect all those deductions were based originally on algorithms, and then someone just inserted the various values into those ratings tables. But I had to engineer backwards. So I took the table 4.6 for organic carbon content and linearized that, depth of topsoil, deductions for density, and depth to the dense layer. I had to develop equations for all those so that I could use them in an Excel spreadsheet. I had to think about appropriate treatments to develop. First of all, what level of change was I going to impose on this design? It had to be realistic. I kind of want to hit the sweet spot of where what is likely happening on pipeline right-of-ways, but without much real reference data, I had to take a wild guess. I decided I would use 10 treatment levels because the number 10 makes everything divide very nicely, and I was looking for that spot where there'd be a threshold change, and I had no idea if I would hit it at level 1 or level 10. So I developed enough little breakpoints along my treatments to find the appropriate resolution. I turned to the Alberta Soil Layer file as baseline. To some extent, it's based on measured data. It's the best database we have for the provincial soils in the white zone. And some of it I know is synthetic, but at the same time, synthetic data is sometimes more useful than measured, more reliable. And then I used mixing equations when I was working with parameters where I'd mix the A and B horizon in proportion to estimate the organic carbon and the particle size distribution as you admix subsoil into the topsoil. So I simply used the values from the A and B horizon as the end members. I chose 6 soil series, knowing that this was for the Alberta Soil Science Workshop. I wanted some from the north, some from the south, and some in between. And so I've got Judah and Beaver Hill soils representing something of the north. Judah is a soil from the Peace River area here, dark gray alluvial. Beaver Hills is around Edmonton, Cooking Lake Moraine area. Hugh Endon and Coaldale are from the dark brown soil zone, and Maleb and Seven Persons are down in the southeast in the brown zone. 2 textural classes, essentially, fine textures and moderately fine. Fine texture glacial lacustrine for 3 of them, and essentially moderately fine till for 3 of these types. And the moisture deficit gradient's negative 200 around this area in Edmonton, and then down to negative 400. The interim soil rating you can think of as the base value of the soil in terms of its capability. So Judah and Beaver Hills in the north are class 1 soils. Hugh Endon and Coaldale in the middle are, I think that's maybe class 3 or class 4, and definitely Maleb and Seven Persons are class 4 in the far south. So the very best rating those soil profiles have is class 4. I chose to ignore anything coarse textured as well. I wanted to focus on these middle textures. Coarse textured soils have problems of their own, and I thought I'd leave that alone for today's discussion. Next, the treatment levels. I thought an appropriate level of admixture would go from 0 to 50%. 50% maybe is worst case scenario, but sometimes soils that have very thin topsoils are handled when they're frozen. I think it's not a stretch to say that you could get 50% subsoil mixed in. The topsoil depth, as you'll see later, is locked in step with the admixture level, because in this model I've assumed we simply add subsoil to the topsoil. We're not losing any topsoil. So as we're admixing, the topsoils are getting deeper with every level of treatment. And then the bulk density of the subsoil, again, I chose 25% increase over baseline as this seemed like maybe an appropriate maximum endpoint. So overall, a 25% increase in density of the subsoil and a 50% increase in the admixture. Then I took those tables from the ratings manual, table 4.6, plotted the points, developed a regression equation with very high R squared, and then I inserted that equation into my spreadsheet. Did the same for topsoil depth with simply a 1 point deduction for every loss of 1 centimeter of soil, starting at 20 centimeters. Subsoil is a little bit more involved, subsoil density, in that there's a separate rating for every textural class. Since I was working with 3 textural classes, I developed 3 ratings equations. They're more or less linear. There's a little bit of curvilinearity in there I couldn't explain, so I just treated it as a linear equation, very high R squared, and I plugged those regression equations into my homemade Excel table. And then of course, as the topsoils got thicker as they were admixed, the dense subsoil layer got deeper and deeper, and I had to modify those percent deductions based on the depth of that layer using this pretty straightforward equation. So some results. So the point of this graph is to show the deductions that are due to simply admixing subsoil into the topsoil. And I'm taking it from the point of view of what does it do to organic carbon. So as you mix B horizon into A horizon, the effect on organic matter on the left-hand graph depends on what you're starting with. The 7-person soil, an Orthic brown from way down south, the organic carbon of the A and the B is almost identical. So no matter how much B you mix into the A, you're not changing the organic carbon content. Whereas with the Beaver Hill soil around Edmonton, an Orthic black, and so there is quite a bit less carbon in the B than the A. So as you start to admix B horizon into the A, you go from about 4% at baseline down to about a little bit less than 3%. So that has some effect on diluting on the organic matter content of the topsoil, at least for the Beaver Hill and maybe for Judah and Coaldale perhaps. But when you translate that into ratings points on the right-hand graph, it doesn't really add up to very much. The 7-person soil at baseline already has about 11 points of deduction due to its low organic carbon, but that essentially may be changed by half of a point by the time you got to 50% admixture. Maybe a better example looks like, I think it's Beaver Hills at the bottom. No point deductions under baseline and up to a maximum of about 3 points. So a whole lot of work, in other words, a whole lot of work to find very, very limited deduction points due to admixture. So at least based on this set of metrics, admixture does not result in a large decline in deductions. Topsoil depth, as I said earlier, for every centimeter of admixture we added, we got a centimeter deeper. So since deduction points only kick in at less than 20 centimeters, in some cases we started out in baseline with some deduction points, but by the time we got to level 5 or level 10, we were no longer deducting for shallower topsoil. Compaction of the subsoil is where most of the action is happening. On the left-hand graph, I'm showing you 2 examples. Judah kind of at the higher end of the bulk densities for B horizons, and Male kind of at the lower end. So under baseline starting at 1.4 or 1.3. And then as you increase that in 2.5% increments out to level 10, you reach about 1.7 for the Judah soil and about maybe 1.6 for the Maleb. And then if you look over on the right-hand graph, deduction points are already happening for our Judah soil, even at baseline. There's a 15% deduction off the interim rating, even under natural conditions, because it has I suppose it's the BT horizon of the Luvasol that's driving that. And then as you stretch it out to level 10, you're up to about an 80% deduction from your interim rating. So that's taking a big hit for that particular soil. Maleb is not quite as bad, but it's going in the same direction. It just starts later before the deduction points start to happen. And it's approaching a 50% deduction in the interim value by the time it gets to level 10. So yes, as you can see, the ratings are most sensitive, at least for the components I've introduced into this model. They're most sensitive to compaction. And the graphs, both graphs here, Judah and 7 persons, show that if you look on the axis for both, its deduction points now have converted everything into deduction points. And the Judah soil, almost the entire change over those 10 treatments is due to the increase in deductions due to compaction. 7 persons, not quite as much in that organic carbon and topsoil depth deductions were important, but if anything, they were more or less flat. So the reason for change in the 7 persons was, again, mostly due to the compaction of the subsoil. This slide's a little bit out of place, but I thought I'd introduce it to show that the different parameters are weighted differently, and so that will contribute to the overall value of the final rating. I excluded anything related to chemistry, but surface factors, pH and electrical conductance, 80 and 90 points respectively, so those are really highly weighted. If I'd introduced those into this model, well, it would have been a different set of findings. But the structure and consistence organic carbon are really low, have low weightings, 10 and 15 points. So no matter what happens to those topsoils, it doesn't score very highly in the overall rating. The subsurface factors, bulk density, and those chemical parameters, they're highly weighted. So here's an example of one of the soils, the Judas soil from our Peace River country here. Under baseline, it starts out at class 2 soil, and out to level 3 of treatments, it's still class 2. It is trending downward, but it hasn't crossed that threshold yet. Level 4 and 5, it's dropped a class. Level 6 and 7, 8, it's dropped another class. So by the end of the set of treatments, it's dropped 3 classes. It's down to class 5 soil now, and that's almost entirely due to the compaction. All 6 soil series shown together, and this is their normalized value. So this is the change from their baseline, 0 being no change, and then every unit change after that. 3 of the 6 of them dropped up to 3 classes by level 10 or sooner. Beaver Hills and Judah and Coaldale in the south all dropped 3 classes in capability by level 10. On the other hand, Maleb and 7 persons only dropped 1 class, and that class change didn't occur till well out level 5, level 6. And Huenden dropped a class right away. I'm not sure we can attribute any directional trends, north versus south. This is a very small sample size of the provincial soil database. I don't know if this is indicator of a trend or not, but it certainly exposes the range of possible change in land capability just to some of the physical properties. Now, if we'd introduced chemistry, for instance, pH, we could probably, well, we might have shifted that even further than 3 classes. So what does all this mean for monitoring programs? We do tend to focus a lot on topsoils, and particularly on the qualitative physical parameters. Munsell color books, consistence, some structural stuff. Yet, as I showed you, that has maybe 10, 15 points deduction. But the big things are kind of slipping through. The big things being that's the subsoil properties, the density. What's happening with density? Are we measuring it? I know in level 2 reclamation assessments and such, sometimes we bring in chemistry, but for the most part, that's not a regular thing that's monitored. So I do favor quantitative parameters. They are reproducible, and that's a very important word. I've heard the word reproducible used a lot, sometimes beyond where I think it belongs. I take that word very seriously, and if you're saying something is reproducible, you better mean it. What's the implication for the regulatory component? I think that the LSRS system can detect change in the state of a soil system. So it's an objective system. It can be used as a benchmark. It's based on some reductionist science. It's the best system we got. It's designed to work Canada-wide, but it's certainly been applied in Alberta. I like to think of the detection limit. That's an important concept. What level of change can your system actually detect? If you're using quantitative data, such as what I've showed you, you've got a higher resolution. You can detect a smaller degree of change reliably, and that's reproducible. If you're using qualitative data, I'm not so sure that your detection limit is the same, and it might be quite coarse. You might not be able to detect a change in capability until something quite extreme has happened. And I guess the knock on systems like land capability metrics. But if you're not using a capability system like this, if you don't have a defined methodology, then how do you know that your site has reached equivalent capability? The next steps, I'd like to use real-world data. Synthetic data is fine, but I've taken this pretty much as far as I should take it. And the next step would be to obtain some data, pipelines, well pads, doesn't really matter that much, and see where it takes me.